Hello and welcome to another episode of 3-Minute Videos with Nathaniel. Today we will answer question 1A of MAT Oxford 2015. Think of a number, let's call it n, add 1, squared, multiplied by 4, subtract 3. We need to find properties about this number regardless of any starting number. We need to use a tool called modular arithmetic. It's like clock arithmetic, but it has addition. For example, what and subtraction, but it's a little different. Modulo 6 is like you're having a 6-hour clock, and modulo 8 is like you having an 8-hour clock. And we also use modulo 4. So n can have 0, 1 or 2 modulo 3. N plus 1 won't change anything, but n plus 1 squared will change it. It only has modulo 0 or 1 in mod 3, and 4 is the same as 1 in mod 3, so we can just keep our modulos. And subtract 3, no difference. That means you have 0 and 1 as your modulos for 3. One of the statements, statement 5, states that it cannot be 1 less than a multiple of 3, which is true, so we'll mark it here. And another one of these statements, before I move on to the other modulos, is that this number is prime. I mean, it's not prime. Watch, I'll prove it to you. It can be prime. There, I told you, it can be prime with n equals to 1. And how about n modulo 4? N can have 0, 1, 2 or 3. N plus 1, 0, 1, 2, 3. N plus 1 squared, and 0 or 1, 0. So you will just have 0. And then you have 1 as this modulo. Since 4 is 0, so it will literally collapse under the modulo 4 line. How about 0, 7? It will not change anything, but it's a startling fact. Squares only have 3 modulos in base 8. Now this is 0, 4, minus 3, this will become 1 and 5. Since minus 3 in mod 8 using this set is the same as plus 1. Now, one of the statements say that it can be 1 more than a multiple of 8. And another one say it must be 1 more than a multiple of 8. So this statement is false, which is, if I remember correctly, it must be statement 3. False. And statement 4, we're not going to go through it, but it says, statement 1 says it must be odd. And so we see our modulo here in mod 4, it is odd. However, we do get a positive result when it has 1 when it has divided by 4. You might want to check out another amazing property of primes, because if I can give you a prime number, let's say 61, gotta tell you it's written as the sum of 2 squares. It can be written as 5 squared plus 6 squared. And this number can be written as 4n plus 1. In this case, n is 15. Now back to the question. Since statements 1 and 5 are the right statements, we can say that statements 1, 5 correct, and this combination of statements is option E. There you have it. This is a big number game, and we cracked some of its codes using modular arithmetic. Modular arithmetic also has a application in cracking codes, which is why I intended that pun. And it also has applications in the sums of 2 squares. Let me give you something. So let me tell you that any number which has a 4n plus 1 form, it can be written as the sum of 2 squares. 4n plus 3, therefore not. But 4n plus 3 squared becomes 16n squared plus 24n plus 9 equals to a number of the form 4m plus 1. So this can be written as the sum of two squares. And if a number that has the sum of two squares can be written as either 4n, or 4n plus 1, then that means multiples of these numbers can also be written as the sum of two squares. Anyway, I hope you like the trivia about squares and modular arithmetic. Thank you, bye!